Hi everyone, today we're going to talk about calorimetry and heating and cooling curve. This is tied to learning objective from the College Board. The student is able to use calculations to relate energy change associated with heating or cooling a substance to the heat capacity with a phase transition to the enthalpy of fusion and vaporization and with a chemical reaction to the enthalpy of the reaction. And also, students can design and interpret the results of an experiment in which calorimetry is used to determine change in enthalpy of a chemical reaction at constant pressure. Specific heat capacity is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree C. It is in the units of joule per gram Kelvin or joule per gram degree C. Now, water has a relatively large specific heat capacity, which is equal to 4.18, meaning that to raise 1 gram of water by 1 degree C, 4.18 joule of heat is required. Calorimetry is an experimental technique to determine heat transfer in a system, and oftentimes we call it a coffee cup calorimeter. So you notice that we have a styrofoam cup, probably double layered, to contain the chemical reaction. And this is covered with a lid to prevent heat loss. And we have a stirrer to ensure temperature is same throughout the solution. And we have a thermometer to measure the heat increase or decrease in the solution. So the reactant is placed into the water bath in a coffee cup where the chemical or physical reaction will take place. Physical reaction will be dissolving. Chemical can be redox, neutralization, precipitation. The change in the temperature of the water is measured and used to calculate the heat exchange between system and water bath. Remember that the heat gained or lost by the water bath is equal to the heat lost or gained by the system, in which case the water bath is the surroundings. At constant pressure, the enthalpy change is equal to the heat energy at constant pressure. Change in enthalpy of a chemical or physical process can then be calculated. To calculate heat when there's a temperature change, we use Q is equal to ms delta T, where Q stands for quantity of heat in joules, M stands for the mass of the solution in grams, that includes the mass of the solute, and the delta T is the change in temperature in degrees C, which is final minus initial temperature. Given the same amount of heat energy, if we have two water samples, the one with the smaller mass will have a larger increase in temperature. Let's say we have 50 milliliter water, given 2,000 joule of heat, the delta T is calculated as 9.57 degrees C. Now, given 100 milliliter water, given the same amount of heat, 2,000 joules, and the delta T is calculated as 4.79 degrees C. Therefore, we conclude the sample with a smaller mass of water has a higher increase in temperature for the same amount of heat energy. Another example is that the substance with a smaller specific heat capacity will have a larger increase in temperature. Now here we have 100 grams of water, and we calculate the delta T to be 4.79 degrees C, given specific heat is 4.18. Now, then we have another 100-gram sample of ethanol with a smaller specific heat, 2.46. The delta T is calculated at 8.13 degrees C. Therefore, we can conclude that in comparing the two substances, given the same amount of heat, the substance with a smaller specific heat capacity will have a larger increase in temperature. Practice problem number 1. Heat capacity of calorimeter. Now, because calorimeter also absorbs heat, therefore we need to find out how much heat is absorbed other than what's happening in the reactant. That means how much heat is also absorbed by the coffee cup. In doing that, we often mix warm water with cold water. Now, let's say we mix 50 grams of water at 75.8 degrees C with another 50 grams of water at 24.8 degrees C. Now, the final temperature is 47. Let's calculate the heat capacity of the calorimeter. The heat released by the hot water, which has a negative sign in front, is equal to the heat gained by the cold water as well as the heat gained by the calorimeter. So the Q hot is equal to Q cold plus Q cal. So to calculate the heat released by the hot water, we have negative 50 grams times the specific heat of water, 4.18 times final temperature, 47 minus initial, 75.8 degrees C. Now this is equal to heat gained by the cold water, 50 grams times 4.18 specific heat times final temperature, 47 minus initial, 24.8, plus the heat gained by the calorimeter, which is equal to C times the same temperature change, the C being the heat capacity of a calorimeter. Therefore, solving the problem, the heat capacity of this calorimeter is 62.1 joule per degree C. Let's say we want to find the specific heat of a metal. First, we take 25 grams of silver metal, we heat it up to 100 degrees C in boiling water. Then we take it out quickly and transfer to another beaker containing 150 grams of water, initially at 20 degrees C. The final equilibrium temperature is 20.8. Using this information, calculate specific heat of the silver metal, assuming there's no heat loss to the environment. Now the heat released by the hot silver is equal to heat gained by the cold water, which has a negative sign in front of the heat released by the hot silver. Negative 25 grams of silver times specific heat of silver times final 20.8 degrees C minus initial 100 degrees C is equal to heat gained by 150 grams of water, specific heat 4.18 times final 20.8 minus initial 20 degrees C. Now, once we have the negative sign in front of the heat released by the hot silver, even though our delta T will be negative on the left-hand side, the negative times negative will be positive. So now we calculate the specific heat of silver being 0.25 joule per gram degree C. The units are important. In melting and in vaporization, the processes are endothermic. Energy is required to overcome the intermolecular forces to separate the molecules apart. The enthalpy of vaporization is defined as energy needed to vaporize 1 mole of a liquid at 1 atmospheric pressure. The enthalpy of fusion is defined as energy needed to melt 1 mole of a solid. For water, the enthalpy of fusion is 6.02 kilojoule per mole, while the enthalpy of vaporization is 40.7 kilojoule per mole. Notice that the enthalpy of vaporization is much, much larger in magnitude than the enthalpy of fusion. This is because much greater amount of energy is required to overcome all of the intermolecular forces in liquid water to turn them into gas molecules. Now let's look at the heating curve and the cooling curve. A heating curve is a plot of temperature versus time for a process when energy is added at a constant rate. The temperature increases during a single phase, and heat can be calculated using the formula Q is ms delta T. However, during a phase change, changing from solid to liquid or from liquid to gas, there are 2 phases present. The temperature does not change and it remains constant because the heat added is used to overcome the intermolecular force to pull molecules apart. To calculate the heat, we have to use the enthalpy, the molar enthalpy of change, times the moles of the substance. When we go to a cooling curve, it would just be the reverse process of a heating curve where heat is removed. Practice problem number 3. Calculate the total energy required to convert 10 grams of ice at negative 4 degrees C to 105 degrees C of steam. Now here we look at the diagram, we plot it, and we identify the different segments. Given the specific heat of ice is 2.03 joule per gram degree C, specific heat of liquid is 4.18, and specific heat of steam is 2.0. So we plot the heating curve and identify the segments into 5, and then we're going to calculate them one at a time. For the segment A to B and solid phase, the 10 grams of ice, specifically 2.03, and it went from negative 4 to finally 0 degrees C. The heat is calculated at 81 joule, and we convert it into kilojoule. For the B to C segment, where we have a phase change, solid to liquid, temperature is not changing, we have Q is equal to 6.02 times the moles, which is 10 grams converted into moles, and we now have 3.34 kilojoule of heat. For segment 3, C to D, the liquid phase, Q is calculated as 10 grams of water times specific heat 4.18, and the water changed from temperature 0 to 100. Therefore, the Q is 4180 joule or 4.180 kilojoule. For segment 4, D to E, when there's a phase change of liquid to gas, we have 40.7 kilojoule per mole. This is the enthalpy of vaporization times the moles, 10 grams converted into moles. We have 22.6 kilojoule of heat. For the final segment, we have pure gas phase, 10 grams of gas, specific heat 2.0 times the temperature change from 100 to 105, and it ends out to be 0.1 kilojoule. Now we can add up the total Q, which is all the 5 components added together in kilojoule unit. We have 30.3 kilojoule of heat. To sum up what we have learned today, we learned how to use the technique of calorimetry to determine heat transferred. We determined the heat capacity of a calorimeter by mixing cold and hot water together. We related specific heat to change in temperature, and we calculated heat quantity for a heating curve. I hope that you have found this video helpful. If you like it, please give us a like, and I look forward to seeing you in the next part of the same video.